Okay, entropy in the second law of thermodynamics is going to be a quick discussion. Okay, so I don't want to beat up entropy too much, but it actually plays into whether reactions are going to work or not. So when we talk about this, the second law of thermodynamics states that any spontaneous process, there's always an increase in entropy. So we are looking for an increase in entropy, okay? Entropy always increases, so whenever it doesn't increase, that's usually when there's trouble or when the reaction is not correct as it's written. Or, I'm sorry, won't work as written, okay? So if we take a look at this total energy of the system versus the surroundings, we have this situation here. Again, I don't think this is the big deal that we're looking for, but again, the sign on delta S is actually quite important. Okay, the sign we're looking for a positive delta S, not a negative delta S, in order for the reaction to proceed as normal. Okay, so for example, if I were to take some H2, and I know I go back to this equation quite a bit, but it's a nice simple one. If I have H2 plus O2 yields H2O, and I need two of these and two of these, as long as I throw a spark on this, okay, actually let me put the spark here, throw a spark here, bang, it goes to the right. It is product favored, okay? So once I get over that activation energy and this thing works and it goes and it produces liquid water, okay, or gaseous water, that is a spontaneous process. That is a positive delta S, okay, positive delta S, okay, because it works on its own, okay? So again, because that works, positive delta S. Now, will water spontaneously become the two gases? Will it naturally break down? We know that not to happen, so that will be a negative delta S, okay? So as it's written this way, it works as long as the spark is in, okay? The reverse is a negative delta S, okay? So notice here as we go further, standard molar entropy values are calculated from absolute entropy values. Again, we're looking at standard states again. There they are listed. Now, because all entropy values for substances are reported relative to absolute zero, elements, everything, in other words, has an entropy value. Okay, period. The units for delta S are now, these are different, are joules per kmol. Joules per kmol. Okay, joules per K times Kelvin times moles, joules per kmol. That's different because you're going to find that you see that delta H is kilojoules per mole, and you'll find something we'll talk about in for delta G, for Gibbs free energy, is in kilojoules per mole. This one's different. It's in joules per kmol. Okay, so there has to be you have to worry about the kilojoules versus joules. Okay. Okay, now don't forget delta H for elements is 0. But delta S, or in other words, change in entropy for elements and everything, will have some type of positive value. So here's a bunch of positive values, okay? And if we take a look at these, again, you don't have to write any of these down, but they're all positive because each of these substances increases as temperature increases, okay? So it's all measured relative to absolute zero, so everything will have some entropy. Okay. Notice solids and liquids have lower entropy than gases. Okay, that makes sense based on our last video. Again, this is that graphic again, but particles, they have no fixed positions here, so they have tremendous amount of disorder, a tremendous amount of entropy, where solids do not. Okay, moving from this way to this way under normal conditions, for example, water evaporating so as it goes from solid liquid to gas, or at least liquid to gas, I suppose, is a positive delta S. Okay, now it can happen, but under normal, at least warm conditions, this doesn't happen so much. So that's definitely a negative delta S. And water vapor rarely, if anything, again, this is a temperature dependent process, but water vapor rarely becomes, at room temperature, ice, so that is a negative, definitely a negative delta S. So actually ice would actually more randomly become water vapor, or at least liquid, and then to water vapor, more often. Geez, I couldn't get the word out. Okay, moving on. Okay, so I didn't want to include this slide. So which of the following phases changes would result in a change in increase in entropy? So we're looking to increase entropy. Again, pause when you need to, but the correct answer is A. Okay. This one, in which of the following instances would entropy increase? Here's all your examples, or here's all the answers, and the correct answer is D. In this one, compare the entropies of KOH solid and KOH aqueous. Which one has the larger entropy? In other words, which situation will the KOH spread out? Okay? In this case, if you have solid KOH, they're locked in bonds, very low entropy, very low disorder. Now, KOH aqueous is definitely more because now they're all spread out, they're all random and everything. I believe the correct answer is B. Okay, now with this one, it says seltzer is a solution of carbon dioxide and water. For the system below, what would you expect the entropy change to be when carbon dioxide dissolves? Okay, so if I have carbon dioxide gas, which comes from seltzer, and now it dissolves in water, now this gas is now dissolved, okay? These have more entropy than these. So the correct answer here is A, in which this process, as it's written, to become to go to the right is not very probable. In other words, this would rather stay as a gas and float away, not become locked in hydrogen bonds in CO2 or perhaps dipole-dipole forces of attraction. More on that later. So that's definitely not a thing that's going to spontaneously happen. Actually, so what happens is this would happen more. This would happen more to the left. So negative to the right, positive to the left. Okay, I'll let you guys write this down. And again, this is something else you can write here. Okay, let's look at this real quick. Actually, look at whether the number of gas molecules is increasing or decreasing. So notice, under normal situations, I go from 2 moles of gases to 3 moles of gases. This is spontaneous to the right. So again, more entropy to the right, okay? Oh, I'm sorry. I don't know whether it's spontaneous or not, but the entropy increases as you move to the right as I drew the green arrow. Therefore, this is a higher probability of being spontaneous, but again, I don't know whether SO3 decomposing to solid sulfur and oxygen is 3 moles of oxygen is a spontaneous process. I just know the randomness increases. So again, we're just looking at whether the number of gas molecules is increasing or decreasing during a reaction. And again, so that's an increase in entropy. This is a decrease in entropy. I go from 3 moles of gas down to 2, and again, negligible because they're the exact same moles of gas on the left and the right. Okay. Lastly, is one of the substances dissolving in a solvent or precipitating from a solvent. So check out what's happening here in these situations. We have an increase in entropy because it becomes aqueous. We have an increase in it. Let's look at this one. We have an increase in entropy when it becomes from an aqueous to a gas, and we have decreases in these two situations here. Okay, you guys can look through these. I'll show you the answers. There is the answer with a little note. Here is the answer, C. In this one, it's C. And then we'll stop there. Next video is actually calculating entropy changes, another simple process. Email me with questions.